Hello, and welcome back. Tonight, there is nothing you need to solve, nothing you need to finish, nowhere you need to be. The solar system has been turning for 4.6 billion years, and it will continue turning whether we hurry or not. So let your breathing slow, let your shoulders settle. Imagine yourself drifting gently above the plane of the planets, watching their quiet paths around the sun. This is not a race across space, but a soft unfolding. One world at a time, one steady orbit at a time. And we will move slowly together into the calm mechanics of our celestial home. At the center of everything we call home stands the Sun, holding about 99.86% of the solar system's total mass. That number is almost difficult to absorb. It means that every planet, every moon, every asteroid, every grain of dust combined makes up only a tiny fraction of what the Sun contains within its luminous sphere. The planets feel dominant to us because we live on one, but in truth, they are delicate companions circling something vastly greater. This concentration of mass is the reason the solar system holds together so gracefully. Gravity flows outward from the Sun like an invisible architecture, guiding the paths of planets into stable ellipses. Without that immense gravitational anchor, Earth would not orbit in calm repetition. Jupiter would not sweep through its long years. The distant icy bodies would drift untethered into interstellar darkness. And yet, despite containing nearly everything, the Sun does not appear crowded or heavy. From afar, it shines with steady simplicity, a sphere of plasma quietly balancing the motion of worlds with nothing more than gravity and time. Light feels intangible. It warms the skin. It brightens a room. It paints the sky at dawn. But sunlight carries momentum. Each photon streaming outward from the Sun possesses a tiny push. Individually, that push is almost unimaginably small, yet across vast distances and over long stretches of time it becomes meaningful. This gentle pressure from sunlight can nudge dust particles into new paths. It shapes the fine tails of comets so that they always stream away from the Sun. It influences delicate grains in the inner solar system, slowly redistributing them in spirals of light. Engineers even design spacecraft concepts with reflective sails, intending to let sunlight itself become propulsion. There is something quietly beautiful about that. The Sun does not only pull through gravity, it also pushes with radiance, a steady outward breath of energy that shapes matter in subtle ways. Even in emptiness, even across millions of kilometers, light is never entirely passive. It carries motion within it, whispering against everything it touches. When we imagine the Sun, we often picture a smooth, glowing disk, but its visible surface, called the photosphere, is anything but still. It is patterned with vast cells known as granules, convection currents where hot plasma rises, cools slightly and sinks again. Each granule can span roughly 1,000 kilometers across, larger than many countries on Earth. These patterns shift constantly. Plasma rises from deeper layers, releasing heat that began its journey hundreds of thousands of years earlier in the core. As it cools, it darkens slightly and descends, replaced by new upwelling currents. The result is a slow, roiling texture, like a luminous ocean in perpetual simmer. Yet, from our distance, it appears serene. The boiling is silent to us. The motion is too fine to notice without instruments. It is a reminder that even the calmest glow can conceal intricate movement. Beneath steady light lies endless circulation, a quiet engine of heat and flow that sustains every orbiting world. Unlike Earth, the Sun is not a rigid sphere. It is made of plasma, ionized gas woven with magnetic fields. Because of this, different parts of the Sun rotate at different speeds. The equator completes a turn in about 25 Earth days. The poles take closer to 35 days. This difference is called differential rotation. It stretches and twists the Sun's magnetic field lines over time, winding them tighter and tighter. Eventually, these tangled magnetic fields can snap and reconnect, producing bursts of energy that ripple outward into space. But even this uneven turning is not chaotic. It follows rhythms. It unfolds in cycles. The Sun's rotation is a layered dance, guided by physics rather than rigidity. It is not spinning like a stone, it is flowing like a current. And in that fluid turning lies the origin of sunspots, solar cycles, and the subtle breathing pattern of our star's magnetism. We often picture the solar system as fixed in place, planets orbiting the Sun in quiet repetition. But the entire system is traveling together through the Milky Way. It moves within a region of space shaped long ago by ancient stellar explosions, inside a cavity of thin, hot gas known as the local bubble. The Sun drifts through this environment at tremendous speed, carrying Earth and every other planet along with it. We do not feel this motion. There is no wind, no resistance. Space offers no friction to slow the journey. And so we sail silently through a vast interstellar landscape. This means our home is not anchored to a single cosmic address. It is part of a larger story, one of stellar births and deaths, of shifting galactic arms, of clouds and voids that stretch across light years. Even as we rest beneath the night sky, we are moving, gently, constantly, through the quiet currents of the galaxy itself. Around each planet lies an invisible boundary called the Hill Sphere. Within this region, the planet's gravity is stronger than the Sun's pull on nearby objects. It is the quiet territory where moons can exist safely, circling their planet instead of being drawn away into solar orbit. The size of this region depends on distance from the Sun and the planet's mass. Jupiter, immense and distant, commands a vast hill sphere, large enough to host dozens of moons and countless small bodies. Earth's is smaller, yet still spacious enough to hold the moon securely in its steady path. This gravitational balance is delicate. Too close to the Sun, and a planet's influence shrinks. Too small, and it cannot keep companions for long. But within these invisible borders, miniature systems take shape. Moons rise and set. Shadows sweep across surfaces. Each planet becomes, in its own way, a quiet center of motion. If you stood on the near side of Earth's moon, the planet would hang in nearly the same spot in the sky, barely shifting. This is because the moon is tidally locked. It rotates once on its axis in exactly the same time it takes to orbit Earth. This phenomenon happens when gravitational forces gradually slow a moon's rotation until it matches its orbital period. Over millions of years, the tug between planet and satellite smooths out irregular spins, settling into synchronized motion. The result is a stable, almost meditative alignment. Tidal locking is common throughout the solar system. Many moons around gas giants are similarly bound. Even some planets beyond our system are likely locked to their stars. It is a reminder that gravity does not only pull, it shapes rhythm, it molds rotation into repetition. And in that repetition, worlds present one face forward, forever turned toward the body that holds them close. Planetary orbits are not circles but ellipses, and this shape creates subtle variation in speed. When a planet approaches its closest point to the Sun, called perihelion, it moves slightly faster. When it reaches its farthest point, aphelion, it slows down. This shifting speed follows a precise mathematical law first described by Johannes Kepler in the early 17th century. The rule is simple. A line drawn between a planet and the Sun sweeps out equal areas in equal times. The consequence is gentle acceleration and deceleration, like a breath expanding and contracting. Most of the time, these changes are subtle. Earth's orbit is nearly circular, so our speed difference is modest. But the principle holds for all planets. Motion is not uniform, it is responsive to distance. Even in the vastness of space, the dance between gravity and velocity continues with quiet precision, adjusting step by step around the central star. Of the 8 major planets, Mercury follows the most elliptical path. Its orbit stretches noticeably compared to the nearly circular tracks of Venus and Earth. This means Mercury experiences a significant difference between its closest and farthest distances from the Sun. At perihelion, Mercury is intensely warmed by solar radiation. At aphelion, it drifts farther away, though still much closer to the Sun than any other planet. This elongated path also contributes to complex patterns of solar heating across its surface. The shape of Mercury's orbit reflects the early gravitational sculpting of the solar system. Interactions with larger planets, particularly Jupiter, have subtly influenced its motion over billions of years. Yet despite this stretched geometry, Mercury's path remains stable. It loops faithfully around the Sun, tracing the same elongated ellipse again and again, bound by gravity in a quiet repetition that has endured for eons. Today, Mars appears dry and austere. Its surface is shaped by dust, rock, and cold, but across its terrain lie unmistakable signs of ancient water. There are branching river valleys carved into highlands. There are delta formations where sediments once settled into standing lakes. There are minerals that form only in the presence of liquid water. Billions of years ago, Mars likely had a thicker atmosphere and warmer conditions. Water may have flowed across its surface, pooling in basins and carving channels that still remain visible from orbit. Over time, as the atmosphere thinned and the planet cooled, surface water disappeared or retreated underground. What remains is a record etched into stone. The dried channels do not move, the deltas do not shift. But they whisper of a time when Mars was more dynamic and perhaps more Earth-like. In the quiet red deserts of today, the memory of ancient rivers still rests beneath the dust. When the sun sets on Mars, the sky does something unexpected. Instead of deepening into warmer shades of orange and red, the horizon near the sun glows with a soft bluish tint. It is a reversal of what we experience on Earth. This happens because Martian dust particles are extremely fine. During the day, they scatter red light across the sky, giving Mars its butterscotch tone. But at sunset, as sunlight travels through more of the atmosphere, the dust preferentially scatters red light away from the sun's direction, allowing cooler blue light to concentrate near the horizon. The result is a small halo of blue around a descending star. It is a quiet optical inversion, a reminder that color depends not only on light itself, but on what that light passes through. On Mars, even the end of the day feels slightly unfamiliar. The sun sinks into a blue glow, and the desert cools beneath a sky that behaves by the same physics, yet tells a different story. The asteroid belt may appear chaotic at first glance, but it carries structure. Many of its rocky bodies belong to distinct families, clusters of fragments that share similar orbits and compositions. These families formed long ago when larger parent asteroids shattered in collisions. When an impact occurs in space, the debris does not scatter randomly forever. Gravity and momentum preserve patterns. The fragments continue orbiting the Sun along similar paths, like pieces of a once whole body traveling together across millions of kilometers. Over time, these groupings remain detectable to astronomers. Each family is a quiet fossil of an ancient collision. By studying their composition and motion, scientists can reconstruct events that happened billions of years ago. The belt is not simply a collection of rocks. It is an archive, a slowly drifting memory of impacts, breakage, and reassembly, preserved in orbital patterns that still hold the signature of their origins. Not all asteroids are loose piles of stone. Some are dense and metallic, composed largely of iron and nickel. These objects may be fragments of the cores of early protoplanets, bodies that once began to differentiate into layered worlds before catastrophic impacts tore them apart. In the early solar system, heat from radioactive decay and collisions allowed some growing bodies to partially melt. Heavier elements sank inward, forming metallic cores, while lighter materials rose toward the surface. If such a body was later shattered, its internal layers could be exposed to space. Metal-rich asteroids are therefore more than rocks. They are remnants of planetary interiors, frozen in time. They carry clues about the processes that shaped the terrestrial planets. Within their dense metallic structures lies evidence of melting, segregation, and early formation, silent witnesses from a time when worlds were still assembling themselves from dust and fire. Jupiter's appearance is defined by alternating bright and dark bands stretching across its surface. These stripes are not static markings. They are the visible expression of immense jet streams racing through the planet's upper atmosphere. These east-west winds reach speeds of hundreds of kilometers per hour, separating lighter zones from darker belts. Rising and sinking gases create differences in color and chemistry. Ammonia ice crystals brighten some regions, while deeper, more complex compounds darken others. Unlike Earth, Jupiter has no solid surface to interrupt these flows. Its atmosphere transitions gradually into deeper layers of fluid hydrogen under extreme pressure. The jet streams persist because there is little friction to slow them. Over centuries, they maintain their structure, carving Jupiter's face into layered motion. It is a world where weather becomes architecture. Not brief storms alone, but long-standing rivers of wind sculpting a planet made mostly of gas. On Saturn's moon Titan, vast dune fields stretch across the equatorial regions. At first glance, they resemble desert landscapes on Earth, long parallel ridges shaped by steady winds. But the sand grains forming these dunes are not made of silica rock. Instead, Titan's dunes are composed of complex organic molecules, hydrocarbons formed in the Moon's upper atmosphere when sunlight breaks apart methane and nitrogen. These molecules fall like soot, accumulating over time. Winds then sculpt them into dunes that can extend for hundreds of kilometers. Titan's atmosphere is thick and hazy, filtering sunlight into a dim amber glow. Within that muted light, organic sand shifts slowly under alien winds. It is a landscape both familiar and profoundly different, a reminder that chemistry, under the right conditions, can build terrains from materials that on Earth would never gather into deserts at all. Titan is the only moon in the solar system with a dense atmosphere, and within that thick orange haze, something quietly extraordinary happens. Methane behaves there the way water behaves on Earth. It evaporates, condenses into clouds, falls as rain, and gathers into rivers and lakes. Near Titan's poles, vast seas of liquid methane and ethane stretch across the landscape. Some are larger than Earth's Great Lakes. River channels branch and wind through valleys, emptying into dark, reflective basins. Shorelines shift over time, shaped by seasonal cycles, but the temperatures are unimaginably cold, around -180 degrees Celsius. Water ice is as hard as stone. The flowing liquid is not water at all, but hydrocarbons moving through an alien climate system. And yet, the patterns feel familiar. Clouds gather, rain falls, liquids carve channels. Even here in the outer reaches of the solar system, cycles repeat. Chemistry changes, but the rhythm of weather remains. Saturn's moon Iapetus presents one of the most striking contrasts in the solar system. One hemisphere is dark as charcoal, absorbing sunlight and appearing almost black. The other is bright and icy, reflecting light with stark brilliance. The leading side of Iapetus, the side that faces forward along its orbit, has accumulated darker material over time, likely from dust drifting inward from other moons. This dark coating absorbs more heat, causing surface ice to sublimate and migrate toward colder regions. There it refreezes, brightening the opposite hemisphere. The result is a feedback loop. Dark becomes darker, bright becomes brighter. From a distance, Iapetus looks divided cleanly in half, like a world painted in shadow and frost. It is a quiet lesson in thermal balance and orbital motion. Even slight differences in sunlight can, over millions of years, sculpt dramatic contrasts across an entire moon. Among Uranus's moons, Miranda stands out for its unusual terrain. Its surface appears fractured and patched together, as though pieces of crust were broken apart and fused back into place. Miranda contains enormous cliffs, vast fault lines, and strange oval-shaped regions called coronae. Some of its cliffs rise more than 20 kilometers high, among the tallest known in the solar system. These features suggest that Miranda may have undergone dramatic internal heating long ago. One possibility is that tidal forces from Uranus briefly warmed the moon's interior, causing partial melting. As the interior shifted and cooled, the surface fractured and reformed. The result is a landscape that does not look smooth or uniform, but layered and complex. Miranda is small, yet its geology speaks of upheaval and recovery. A moon that carries the memory of disruption etched across its surface. Pluto and its largest moon, Charon, are so similar in size that they do not behave like a typical planet-moon pair. Instead, they orbit a shared center of mass, a barycenter located in empty space between them. As they revolve, both bodies circle this invisible point. From Pluto's surface, Charon would appear enormous in the sky, locked in place above one region due to mutual tidal locking. The two worlds are gravitational partners bound in synchronized rotation. This binary-like system formed long ago, likely from a massive collision that sent debris into orbit. Over time, that debris coalesced into Charon. Today, they move together in slow repetition, neither fully dominant over the other. It is not a hierarchy of planet and satellite, but a shared dance. two frozen bodies turning around a common balance in the quiet darkness beyond Neptune. On very dark, moonless nights, far from city lights, a faint glow can sometimes be seen stretching upward from the horizon before dawn or after dusk. This soft triangular glow is called the zodiacal light. It is not a distant nebula or a hidden galaxy. It is sunlight reflecting off fine dust particles that fill the inner solar system. These grains are remnants of asteroid collisions and comet debris, suspended in orbit around the Sun. Individually tiny, collectively they scatter enough light to become visible under the right conditions. The glow aligns with the ecliptic plane, the flat disk where most planets orbit. It is a reminder that space is not entirely empty. Between the worlds, dust drifts quietly, illuminated by the Sun's steady radiance. Even in the spaces between planets, there is structure. A faint shimmer of light tracing the invisible architecture of our solar neighborhood. Among Jupiter's many companions, 3 of its largest moons, Io, Europa, and Ganymede, are linked in a precise gravitational pattern known as orbital resonance. For every 4 orbits Io completes, Europa completes 2, and Ganymede completes 1. This ratio is not accidental. It is maintained by the steady pull they exert on one another as they circle their planet. This gravitational rhythm prevents their orbits from becoming perfectly circular. Instead, each moon is gently stretched and released as it moves closer to and farther from Jupiter. That subtle flexing generates internal friction and heat, shaping their geologies over time. Resonance is a quiet sculptor. It does not break worlds apart, but it keeps them dynamically active. Through simple ratios and repeating motion, gravity links distant bodies into synchronized patterns. Across hundreds of thousands of kilometers, the moons remain in step, orbit after orbit, guided by forces that require no sound, only balance. Not all objects that travel near planets are moons. Some occupy stable regions of space called Lagrange points, areas where gravitational forces from a planet and the Sun balance in such a way that small bodies can remain in steady orbit. These objects are known as Trojans. Jupiter hosts thousands of them, clustered ahead of and behind it along its path around the Sun. Earth also has a few small companions in similar configurations, though they are faint and temporary compared to Jupiter's vast populations. Trojans are not bound directly to the planet itself. Instead, they share its journey, orbiting the Sun in synchrony. They are quiet fellow travelers, held in place by delicate gravitational equilibrium. In the broad architecture of the solar system, even small pockets of stability can endure for millions of years. Between Jupiter and Neptune lies a population of small icy bodies known as centaurs. Their orbits are unstable on long timescales, crossing the paths of giant planets and slowly evolving under gravitational influence. Centaurs are transitional objects. Some originate in the outer reaches of the solar system and drift inward. Others may eventually become short-period comets if gravitational encounters alter their trajectories. Their surfaces often show signs of both asteroid-like and comet-like behavior. These bodies exist in a state of quiet impermanence. Their paths are not as settled as those of the major planets. Over millions of years, close encounters with giant planets can scatter them inward, outward, or eject them entirely. They are wanderers of the middle regions, moving between stability and change, shaped by gravitational nudges that accumulate slowly over time. Despite the brilliance of a comet's glowing tail, its core, the nucleus, is remarkably dark. Many comet nuclei reflect only a few % of the sunlight that strikes them. Their surfaces are coated with complex organic materials formed by long exposure to radiation in deep space. These nuclei are often only a few kilometers across. They are mixtures of ice, dust, and rocky material loosely bound together. When they approach the Sun, heat causes ices to sublimate, releasing gas and dust that form the familiar coma and tail. But at great distances, far from solar warmth, a comet nucleus drifts quietly, almost invisible. It absorbs more light than it reflects. It carries within it ancient material preserved from the early solar system. Beneath the spectacle of bright tails lies something subdued, a dark, fragile body holding the memory of the system's earliest chemistry. Before there were planets, there was a vast cloud of gas and dust collapsing under its own gravity. As it contracted, it began to spin faster, flattening into a rotating disk. At the center, pressure and temperature rose until nuclear fusion ignited, forming the Sun. Within the surrounding disk, dust grains collided and stuck together. Small clumps grew into larger bodies through accretion. Over millions of years, these building blocks assembled into planetesimals, then protoplanets, and eventually the worlds we know today. The disk's rotation set the direction of planetary orbits. The flatness of the disk explains why most planets travel along nearly the same plane. From turbulence and collision, order gradually emerged. The solar system's structure, its shared direction of motion, its layered arrangement of rocky and giant planets, still reflects that original spinning disk. Even now, billions of years later, the imprint of its formation remains written in orbital paths. Jupiter is immense, more than 11 times wider than Earth, yet it completes one full rotation in just under 10 hours. This rapid spin makes it the fastest rotating planet in the solar system. Because Jupiter is made primarily of gas and fluid layers rather than solid rock, its swift rotation causes it to bulge at the equator. The planet is noticeably flattened, wider around its middle than from pole to pole. Centrifugal force stretches its shape outward, while gravity pulls inward, creating a subtle but measurable distortion. This speed also influences Jupiter's weather. The rapid turning strengthens jet streams and organizes its atmospheric bands into long parallel stripes. The entire planet behaves like a colossal spinning sphere of fluid dynamics. Even something as fundamental as rotation shapes a world's appearance. On Jupiter, 10 hours is enough for sunrise, sunset, and sunrise again, a swift day unfolding on a giant scale. Beyond its contrasting hemispheres, Iapetus possesses another unusual feature, a mountain ridge running almost exactly along its equator. In some places, this ridge rises more than 20 kilometers high and spans a significant portion of the Moon's circumference. The origin of this ridge is still debated. One idea suggests that Iapetus once rotated more rapidly, causing material to accumulate along its equator before the Moon slowed down. Another hypothesis proposes that debris from a former ring system collapsed onto the surface, settling along the equatorial line. Whatever its origin, the ridge gives Iapetus a walnut-like appearance. It is as though the Moon once wore a ring and kept its imprint. The structure stands as a reminder that small bodies can preserve dramatic features for billions of years. With little erosion to smooth them away, ancient shapes remain intact, frozen in time. Ariel, one of Uranus's larger moons, displays long valleys, ridges, and smooth plains that suggest internal reshaping long ago. Its surface is brighter than many neighboring moons, indicating resurfacing events that replaced older, heavily cratered terrain. These features likely formed when internal heating caused parts of Ariel's icy crust to fracture and shift. Expanding materials may have pushed outward, cracking the surface into chasms. In some regions, smoother material appears to have flowed or settled afterward, filling low areas. Though Ariel appears quiet today, its geology hints at a period of internal energy. Even small moons can experience episodes of activity when tidal forces or residual heat briefly warm their interiors. The result is not chaos but structure, valleys and ridges that trace the Moon's ancient attempts to adjust and release internal stress. While long-period comets may take thousands of years to return, others follow much shorter cycles. These are known as Jupiter family comets, and many complete an orbit around the Sun in less than 20 years. Their paths have been shaped by close encounters with Jupiter, whose gravity can capture and reshape trajectories. Over time, these comets settle into shorter, more predictable orbits. Each return to the inner solar system gradually reduces their volatile material as ices sublimate away. With every pass, they lose a little more mass. Jets carve pits into their surfaces. Dust trails accumulate along their orbital paths. Eventually, some fade into inert, rocky remnants. Their lives are cyclical, but not eternal. Orbit by orbit, they change. The solar system does not stand still, even when motion appears repetitive. As the solar wind flows outward from the Sun, it eventually encounters resistance from the interstellar medium. At a certain distance, this outward flow slows dramatically, forming a region known as the termination shock. Beyond this point, the solar wind continues but at reduced speed, eventually reaching a boundary where it yields to interstellar pressure. This creates a vast bubble around the solar system, shaped by motion through the galaxy. The boundary is not sharp like a wall. It is a gradual transition, defined by changing particle speeds and magnetic fields, yet it marks a meaningful threshold, the place where the Sun's constant outward breath begins to lose dominance. Even stars have limits to their reach, and somewhere far beyond the planets, the Sun's influence fades into the quiet medium between stars. Vesta is one of the largest objects in the asteroid belt, and unlike most asteroids, it once began the process of becoming a fully differentiated world. Early in the solar system's history, heat from radioactive decay warmed its interior enough to separate into layers: a metallic core, a rocky mantle, and a crust. This internal differentiation is something we associate with planets, yet Vesta never grew large enough to clear its orbital neighborhood or continue evolving into a major planet. Instead, it remained suspended in developmental stillness. A colossal impact later carved out a massive crater near its south pole, exposing deeper layers and sending fragments into space. Some of those fragments eventually fell to Earth as meteorites. In this way, pieces of Vesta's ancient interior have been studied in laboratories. It is a world that almost was, a planetary blueprint preserved in miniature. Between the planets lies a persistent haze of microscopic particles known as interplanetary dust. These grains originate from asteroid collisions and comet outgassing. Though individually tiny, together they form a subtle, ever-present cloud within the inner solar system. This dust is responsible for phenomena like zodiacal light and faint background glows seen by sensitive instruments. Over time, dust particles spiral slowly inward toward the Sun due to a process called Poynting-Robertson drag, where sunlight subtly alters their momentum. The space between planets is not empty. It is textured, layered with drifting material that reflects ancient collisions and ongoing fragmentation. Each grain traces an orbital path shaped by gravity and light. In the vast distances between worlds, even dust participates in the long choreography of motion. Ceres, the largest object in the asteroid belt and classified as a dwarf planet, possesses intriguing bright patches on its surface. These regions were revealed by spacecraft observations to be deposits of sodium carbonate and other salts, materials typically left behind when briny water evaporates. This suggests that beneath Ceres's surface, liquid brines may once have existed, or perhaps still persist in pockets below the crust. Unlike dry, rocky asteroids, Ceres appears to have retained volatile materials, including water ice. The presence of salts hints at a more complex internal history. Even in the asteroid belt, far from the warmth of the inner solar system, chemical processes can produce layered geological features. Ceres is not merely a leftover fragment. It is a differentiated body with its own subtle cycles of freezing, melting, and mineral transformation. When hydrogen fuses into helium in the Sun's core, enormous energy is released in the form of photons. But these photons do not travel directly outward to space. Instead, they embark on a slow, indirect journey. Within the Sun's dense interior, photons are constantly absorbed and re-emitted by particles of plasma. Each interaction alters their direction. Rather than moving straight outward, they wander in a complex, zigzag path. This process can take hundreds of thousands of years before the energy finally reaches the surface. Once released from the photosphere, however, that same energy travels to Earth in just over 8 minutes. There is something humbling about that timescale. The sunlight warming your face began its journey long before human civilization existed. It is ancient energy, finally emerging into open space. Deep within Jupiter's immense pressure, hydrogen behaves in ways that seem almost impossible under Earth conditions. At extreme depths, hydrogen is compressed so tightly that it enters a state known as metallic hydrogen, a phase in which it conducts electricity like a metal. This layer is thought to be responsible for Jupiter's powerful magnetic field. As metallic hydrogen circulates within the planet's interior, electrical currents are generated, producing magnetism on a colossal scale. Unlike the rocky cores of terrestrial planets, Jupiter's internal structure transitions gradually from gaseous to liquid to metallic states under crushing pressure. The boundaries are not sharp. They are continuous shifts in behavior, guided by physics. Inside Jupiter, even the simplest element in the universe takes on unfamiliar properties, shaped by gravity and compression into something entirely different. It may seem intuitive that the Sun, containing almost all the solar system's mass, would also contain most of its motion. Yet this is not the case. While the Sun holds the overwhelming share of mass, the majority of the system's angular momentum, the measure of rotational motion, resides in the planets. This imbalance traces back to the early solar nebula. As the cloud collapsed and flattened into a disk, friction and magnetic interactions transferred much of the system's rotational energy outward. The forming planets inherited that motion. The Sun remained massive, but comparatively slow in spin. There is something quietly elegant in that distribution. The star anchors the system gravitationally, while the planets carry the momentum of its birth. Motion and mass do not always align. The architecture of the solar system reflects a delicate redistribution, gravity pulling inward, rotation spreading outward. A balance established billions of years ago and still preserved today. Though often drawn as a neat dipole stretching evenly from pole to pole, Earth's magnetic field is more complex. It wavers, tilts, and shifts over time. The magnetic poles do not sit directly opposite one another, nor do they remain fixed in place. Within the molten outer core, iron flows in constantly changing patterns. These currents generate magnetism, but the flow is dynamic, not uniform. As a result, the magnetic field fluctuates in strength and orientation. Over geological time, it has even reversed entirely, with north and south swapping places. These reversals are not sudden catastrophes. They unfold gradually across thousands of years. The field weakens, reorganizes, and strengthens again. It is a reminder that even invisible shields are alive with motion. Beneath the crust of our planet, quiet currents maintain a protective field that is steady in effect but fluid in structure. Within the asteroid belt are regions curiously devoid of objects. These empty lanes are known as Kirkwood gaps, and they are shaped by Jupiter's gravitational influence. When an asteroid's orbital period forms a simple ratio with Jupiter's, such as completing 3 orbits for every one of Jupiter's, repeated gravitational tugs accumulate. Over time, these resonances destabilize the asteroid's path, nudging it into a new orbit or ejecting it entirely. The gaps are not caused by collisions or physical barriers. They are the result of rhythm. Repetition of gravitational influence reshapes distribution. Even at great distances, Jupiter's presence is felt as subtle structure within the belt. The asteroid region is not random, it is patterned by resonance, sculpted by predictable cycles of orbital timing. Among the icy moons, Enceladus stands out for its brightness. Its surface reflects nearly all the sunlight that reaches it, making it one of the most reflective bodies in the solar system. This high reflectivity is due to fresh ice covering its surface. Material ejected from internal processes falls back down as snow-like particles, renewing the moon's exterior. Instead of darkening over time from space weathering, Enceladus maintains a gleaming appearance. Brightness in space often signals youth. Fresh surfaces indicate ongoing processes. Though small, Enceladus resists dullness. Its surface is continually refreshed, preserving a pale sheen against the dark backdrop of space. Even in the cold outer regions, activity can maintain brilliance. While the planets orbit the Sun and the Sun moves within its local galactic neighborhood, the entire solar system also participates in a grander motion. It circles the center of the Milky Way, completing one full orbit roughly every 225 to 250 million years. This journey is sometimes called a galactic year. During that span, continents rise and erode, species evolve and vanish, and climates shift. Yet the solar system continues its spiral path around the galactic center, guided by the gravity of billions of stars. We do not feel this motion, there is no sensation of turning, but at every moment, Earth and its companions are moving through the galaxy's vast structure. The night sky appears constant across a lifetime, yet over immense timescales, constellations reshape and positions change. We are part of a larger orbit, tracing a slow arc through the Milky Way's luminous arms. Ganymede, the largest moon in the solar system, possesses something no other moon is known to have: its own intrinsic magnetic field. While many moons exist within the magnetic influence of their parent planets, Ganymede generates a field from within. This suggests the presence of a partially molten conductive layer deep inside, likely a liquid iron or iron sulfide core. As that material moves, it creates electrical currents, and those currents generate magnetism. Around Ganymede, this produces small auroras that shimmer within Jupiter's immense magnetic environment. It is a moon, yet it behaves in certain ways like a planet. Its magnetic field forms a miniature magnetosphere nested inside Jupiter's much larger one. Within layers of ice and hidden oceans, internal structure quietly persists. Even far from the Sun, even under the dominance of a giant planet, a smaller world can sustain its own internal dynamo. Embedded within certain primitive meteorites are microscopic mineral grains that predate the formation of the solar system itself. These tiny particles formed around ancient stars that lived and died before our Sun was born. When the solar nebula collapsed, it incorporated remnants of earlier stellar generations. Most material was reprocessed, melted, and reshaped, but a small fraction survived intact, tiny crystals carrying isotopic signatures of distant stellar furnaces. When these meteorites fall to Earth, they deliver fragments of cosmic history older than our star. Within laboratory microscopes, scientists can study material forged in supernovae and red giant outflows long before our Sun ignited. It is humbling to consider that pieces of ancient stars now rest within stones found on Earth. The solar system did not form from pristine matter. It formed from recycled stardust. Earth's path around the Sun is not perfectly fixed. Over tens of thousands of years, its orbit subtly shifts in shape and orientation. These variations are known as Milankovitch cycles. The eccentricity of Earth's orbit changes slightly, becoming more or less elliptical over long timescales. The tilt of Earth's axis also varies, as does the slow wobble of its orientation, called precession. These changes influence how sunlight is distributed across the planet's surface. Such orbital adjustments have played roles in Earth's ice ages and long-term climate patterns. They unfold gradually, almost imperceptibly within a human lifetime. Yet, across geological eras, these small shifts accumulate into meaningful differences. The orbit that feels steady tonight is part of a slow, ongoing variation, a quiet modulation of geometry and sunlight. The Sun constantly emits a stream of charged particles known as the solar wind. Though thin, this plasma carries magnetic fields and moves at hundreds of kilometers per second. As it flows outward, it interacts with planets, comets, and dust. On worlds without strong magnetic shielding, the solar wind can gradually strip away atmospheric particles. Over billions of years, this process may have contributed to the thinning of atmospheres on smaller planets. Comets, when near the Sun, display ion tails that always point away from it, shaped not by motion alone, but by the pressure of solar wind pushing charged particles outward. The solar system is not static vacuum. It is threaded with invisible currents of plasma shaping surfaces and atmospheres in ways subtle and persistent. Planetary rings are not necessarily permanent structures. In some cases, material within rings can gradually accumulate into small moons if conditions allow particles to clump together beyond a certain boundary known as the Roche limit. Saturn's rings, for example, contain small moonlets embedded within them. Some of these bodies may represent early stages of coalescence, particles gathering under gravity into larger structures. Over long spans of time, ring systems can evolve, shedding material inward or outward. The boundary between ring and moon is not always clear. It is a matter of gravitational balance and orbital stability. Within the delicate interplay of tides and collisions, new bodies can emerge. Even rings are not static ornaments. They are dynamic systems, capable of both erosion and creation. Each day on Earth is not exactly the same length as it was in the distant past. The moon's gravity raises tidal bulges in Earth's oceans. Because Earth rotates faster than the moon orbits, those bulges are carried slightly ahead of the moon's position. The gravitational pull between the bulges and the moon transfers angular momentum outward. As a result, Earth's rotation gradually slows and the moon drifts farther away. Hundreds of millions of years ago, a day on Earth was significantly shorter. Coral growth rings and geological records preserve evidence of this slower spin. The change is subtle, only milliseconds per century, but persistent. Time itself, as measured by the length of a day, is gently reshaped by tidal interaction. The partnership between Earth and Moon is not static, it is a slow exchange of motion unfolding across epochs. Auroras are not unique to Earth. Jupiter and Saturn also display shimmering lights near their poles, produced when charged particles interact with atmospheric gases. But on Jupiter, these auroras are vastly more energetic. Jupiter's magnetic field funnels particles toward its poles with extraordinary strength. Some of those particles originate not from the Sun alone, but from Io's volcanic emissions, which feed material into Jupiter's magnetosphere. The result is a constant, intense auroral glow. Unlike Earth's auroras, which brighten during solar storms and then fade, Jupiter's auroras are nearly continuous. They are powered by internal dynamics as much as by solar activity. In the outer solar system, magnetism and plasma create luminous curtains of light that never fully disappear. Evidence from ancient rocks suggests that Mars once possessed a global magnetic field similar to Earth's. Magnetic signatures locked within its crust indicate that molten material once flowed within its interior, generating a dynamo effect. At some point, however, Mars's internal engine cooled and slowed. Without a strong magnetic shield, the planet's atmosphere became more vulnerable to solar wind stripping. Over billions of years, much of its thicker atmosphere was lost to space. The remnants of magnetism are still detectable in certain regions of Mars' crust. They are like fossilized traces of a time when the planet was more internally active. Though quiet now, Mars once pulsed with a magnetic heartbeat of its own. Certain small asteroids spin at remarkable speeds. Because they are often loosely bound rubble piles rather than solid monoliths, rapid rotation can bring them close to structural failure. If an asteroid spins too quickly, centrifugal forces may exceed the weak gravitational binding that holds it together. In some cases, this can cause surface material to migrate toward the equator, forming a ridge. In extreme cases, fragments may separate entirely. These rapid spins can be accelerated by uneven heating from sunlight, a subtle effect known as the Yorp effect. Over time, absorbed and re-emitted radiation exerts tiny torques. Even light applied persistently can alter rotation. Motion in the solar system is shaped not only by massive forces but by delicate cumulative influences. The current arrangement of planets may not reflect their original positions. Evidence suggests that the giant planets shifted or migrated during the early solar system. Interactions between the young planets and leftover planetesimals could have caused Jupiter and Saturn to move inward or outward slightly. Such migration would have reshaped smaller body populations, scattering objects into new regions and influencing the architecture of the asteroid belt and outer icy zones. This early reshuffling helps explain certain orbital patterns seen today. The solar system was not born in its present configuration. It evolved dynamically, settling into stability only after a period of gravitational rearrangement. The calm we observe now is the outcome of earlier motion and adjustment. For many years, rings were thought to belong only to the giant planets. But in 2013, astronomers discovered that a small object between Saturn and Uranus, a centaur named Chariklo, possesses a pair of narrow rings. These rings were detected not by direct imaging but by observing starlight dimming in precise patterns as Chariklo passed in front of a distant star. The dips in brightness revealed thin bands of orbiting material. The discovery reshaped assumptions about ring formation. Even relatively small bodies can maintain ring systems if gravitational conditions allow. Rings are not exclusive to planetary giants. They are expressions of balance, material caught between falling inward and escaping outward. In quiet orbit, even a minor world can wear a delicate halo. Mimas is small and icy, but its most striking feature is a vast impact crater called Herschel. The crater spans nearly 1/3 of the Moon's diameter. The force required to create such a crater was immense. It likely came close to shattering Mimas entirely. The impact left fractures extending deep into the Moon's interior. Yet Mimas endured. It did not break apart. Instead, it carries the scar as a permanent record of survival. In the vacuum of space, impact marks remain unsoftened by weather or erosion. They persist across geological ages. Mimas is a reminder that even catastrophic encounters can leave a body intact, though forever changed. The Sun is not equally active at all times. Approximately every 11 years, its magnetic activity waxes and wanes in a predictable cycle. During solar maximum, sunspots multiply across the surface. Solar flares and coronal mass ejections become more frequent. Auroras on Earth grow brighter. As the cycle declines towards solar minimum, the surface quiets. This rhythm arises from the Sun's internal magnetic dynamics. Twisting and reconnection of magnetic field lines build gradually, release energy, and then reset. The cycle does not alter the Sun's overall brightness dramatically, but it does modulate space weather. Even our star has seasons of activity and calm. Its surface breathes in magnetism and exhales in flares, repeating a cycle that has unfolded for billions of years. Beneath icy crusts in the outer solar system, liquid water may exist in darkness. Several moons, including Europa, Enceladus, Ganymede, and others, show signs that oceans may lie hidden beneath thick ice shells. These oceans are thought to be kept liquid by tidal heating. As moons are stretched and flexed by gravitational forces, friction generates warmth within their interiors. Though sunlight never reaches these hidden seas, internal energy may provide chemical gradients capable of sustaining complex processes. The idea that oceans can exist far from the Sun expands our understanding of where liquid water can persist. These oceans are unseen, sealed beneath kilometers of ice, yet their presence suggests that life-friendly environments may not be limited to surface worlds alone. Mercury's surface is densely cratered, preserving a record of impacts from the early solar system. Without a thick atmosphere or active plate tectonics to erase features, craters remain visible across vast stretches of terrain. Some basins are enormous, formed by collisions with large bodies long ago. Others are small, scattered impressions marking more recent impacts. The absence of erosion allows scientists to read Mercury's geological history directly from its surface. Each crater is a timestamp of collision. The density and distribution reveal periods of intense bombardment and quieter intervals. In its silence and stillness, Mercury preserves a chronicle of cosmic encounters, a rocky archive orbiting closest to the Sun. Though Neptune appears to travel alone at the outer edge of the planetary system, its gravity subtly shapes the motion of countless distant icy bodies. Many objects beyond Neptune are locked in orbital resonances with it, meaning their periods follow simple ratios relative to Neptune's own. Pluto, for example, completes 2 orbits for every 3 of Neptune's. This resonance prevents close encounters despite their overlapping orbital distances. The gravitational timing keeps them safely out of collision. Resonance is not forceful in a single moment, it is cumulative. Repetition builds stability. Over billions of years, these gravitational relationships organize the outer solar system into patterns of rhythm and spacing. Neptune's steady orbit becomes a metronome for distant bodies, guiding motion through quiet mathematical precision. If we could see the Sun in certain wavelengths of light, we would observe vast arches of glowing plasma rising and falling above its surface. These structures trace magnetic field lines that extend outward, curve, and reconnect. Plasma, electrically charged gas, follows magnetic pathways. As the Sun's interior motion twists magnetic lines, they rise in luminous arcs known as prominences or coronal loops. Some extend hundreds of thousands of kilometers into space before collapsing or dissipating. Though invisible to the naked eye, these magnetic structures shape solar activity. They store energy, sometimes releasing it in flares. Yet most of the time, they simply arch quietly, suspended against the darkness of space. The Sun's surface is not smooth. It is threaded with invisible geometry, revealed only through careful observation. Within Saturn's rings are distinct divisions and narrow gaps. Some are maintained by small moons orbiting within or just beyond the ring system. These shepherd moons use gravity to confine ring particles into sharp edges. As ring particles drift, the moon's gravitational pull nudges them back into alignment. The result is structure where chaos might otherwise prevail. Gaps form where material cannot stably orbit. The The rings appear continuous from a distance, yet up close they are a complex system of countless particles guided by subtle gravitational choreography. Even small moons can carve order into fields of ice and dust, maintaining lanes and boundaries that persist over time. Occasionally, small asteroids are captured temporarily by Earth's gravity, entering orbit for months or even years before escaping again. These transient visitors are sometimes called temporary natural satellites or mini-moons. They are typically small, often only a few meters across, and difficult to detect. Their capture is not permanent. Gravitational interactions with Earth, the Moon, and the Sun eventually alter their paths. These companions are fleeting. They circle Earth quietly for a time, then drift away, resuming solar orbit. Their presence reminds us that gravitational capture does not always mean permanence. The solar system allows for brief partnerships as well as long-standing bonds. In its earliest hundreds of millions of years, the solar system experienced a period of frequent and powerful impacts. Large bodies collided, merging or fragmenting as planets took shape. Craters on the Moon, Mercury, and other airless bodies preserve evidence of this era. Some scientists refer to a particularly intense phase as the Late Heavy Bombardment, though details remain debated. These collisions were not anomalies. They were part of formation itself. Worlds assembled through repeated impact and accretion. Over time, as debris diminished and orbits stabilized, the rate of impacts declined. The calm skies we know today are the product of that earlier turbulence. The scars remain on ancient surfaces, silent reminders of a time when the solar system was still settling into its long-term equilibrium. Jupiter is not silent. Though space carries no sound, Jupiter produces intense radio emissions that can be detected by instruments on Earth. These signals are generated by interactions between its powerful magnetic field and charged particles moving within it. Some of this activity is influenced by its moon Io. Material from Io's volcanic eruptions becomes ionized and trapped within Jupiter's magnetosphere. As these particles spiral along magnetic field lines, they generate radio waves across a range of frequencies. If our ears could translate those frequencies into audible sound, Jupiter would seem active and dynamic. The emissions fluctuate with rotation and magnetic alignment, forming patterns that scientists can study to understand the planet's interior and magnetospheric structure. Even without light, Jupiter reveals itself through invisible signals carried across space. Beyond Neptune lies a broad region filled with icy bodies, extending tens of billions of kilometers from the Sun. This region, known as the Kuiper Belt, is far larger and more complex than the asteroid belt. Within it reside dwarf planets, frozen remnants of early formation, and countless smaller objects. Some follow nearly circular paths, others trace elongated or tilted orbits. The Kuiper Belt is not uniform. It contains clusters, resonant populations, and scattered objects influenced by Neptune's gravity. These distant bodies remain largely unchanged since the solar system's youth. Far from solar warmth, chemical processes slowed dramatically. The Kuiper Belt preserves materials that formed in the outer disk billions of years ago. It is a cold archive, orbiting quietly at the edge of planetary space. On certain icy moons, regions of the surface appear fractured and jumbled, as though large plates of crust broke apart and refroze in disordered arrangements. This chaos terrain suggests dynamic processes beneath the surface. Heat from tidal forces or internal energy may partially melt subsurface layers. When that material shifts, the crust above can crack, tilt, and resettle. The result is a mosaic of blocks separated by ridges and troughs. Chaos terrain is not random destruction. It is the surface expression of internal change. Even worlds covered in ice can experience episodes of restructuring. Beneath a seemingly frozen exterior, movement may continue quietly, reshaping landscapes over immense spans of time. Because the Sun is composed of plasma rather than solid rock, its rotation is not uniform. The equatorial regions complete a rotation in roughly 25 Earth days, while the poles take closer to 35 days. This difference stretches magnetic field lines over time. As the equator turns faster than higher latitudes, magnetic structures become twisted and stressed. Eventually, this contributes to magnetic reconnection events and solar activity. The Sun's rotation is layered and fluid. It does not spin like a rigid sphere. Instead, it flows. different regions move at different rates, creating internal shear that shapes the star's magnetic behavior. Even at the scale of a star, motion remains nuanced rather than uniform. While many asteroids appear dry, certain carbon-rich types contain minerals that formed in the presence of water. These hydrated minerals suggest that liquid water once existed within their parent bodies. Heat from radioactive decay may have melted ice inside early asteroids, allowing water to interact chemically with rock. Though these bodies later cooled and solidified, the mineral signatures remain. When fragments of such asteroids fall to Earth as meteorites, scientists can analyze their chemistry. The presence of hydrated minerals reveals that water was present even in small bodies during the early solar system. Water was not confined to planets alone. It participated in shaping objects large and small during the system's formative era. Not all moons follow the spin of the planet they orbit. A number of smaller satellites, particularly around the giant planets, travel in retrograde orbits, moving opposite the direction of their planet's rotation. These moons were likely not born alongside their host planet. Instead, they were captured long ago, perhaps drawn in from passing populations of icy bodies. Their irregular shapes and tilted, elongated orbits support this idea. Capture is not gentle. It requires energy exchange, often involving early interactions with gas disks or other moons. Yet once settled, these retrograde satellites become long-term companions. Their backward motion is not unstable, merely different. Even within a shared gravitational system, diversity of direction persists. The solar system accommodates both alignment and reversal within its quiet balance. Though it appears steady to us, the Sun's luminosity has increased slowly over billions of years. Early in its history, it was significantly dimmer than it is today. As hydrogen in the core fuses into helium, the core becomes denser and slightly hotter. This increases the rate of fusion, causing a gradual rise in brightness. The change is slow, measured in fractions of a percent per 100 million years, but cumulative. This slow brightening has influenced Earth's climate across geological eras. Long-term shifts in solar output have been balanced by atmospheric changes on Earth that regulate temperature. Even stability evolves. The Sun's calm glow today is part of a gradual transformation unfolding across immense timescales. Icy moons are not always solid blocks of frozen material. In many cases, they contain multiple internal layers: an outer crust of ice, a subsurface ocean, deeper high-pressure ice phases, and rocky cores. Under increasing pressure, water ice changes structure into denser crystalline forms. This means that even beneath an ocean, ice may reappear in compressed states. The internal architecture of these moons is layered and complex. Temperature gradients, tidal heating, and composition determine how these layers arrange themselves. Though hidden from direct view, their existence is inferred through gravity measurements, magnetic signals, and modeling. Beneath smooth, icy exteriors lies stratification, structure shaped by pressure and heat in the cold outer solar system. In any system of two large bodies, such as the Sun and a planet, there exist 5 locations where gravitational forces and orbital motion balance precisely. These are known as Lagrange points. At certain of these points, small objects can remain in stable or semi-stable positions relative to the larger bodies. Space agencies use some of these locations to position observatories, allowing them to maintain steady orientations with minimal fuel use. Lagrange points are not visible markers in space. They are solutions to gravitational equations, quiet pockets where balance emerges from motion. Within the sweeping orbits of planets and stars, geometry creates stillness. Stability is not the absence of motion, but the product of forces in equilibrium. During the solar system's formation, temperature differences within the protoplanetary disk played a critical role in determining planetary composition. Closer to the young Sun, temperatures were too high for volatile compounds like water, methane, and ammonia to condense. Farther out, beyond a boundary sometimes called the snow line, ices could form and remain stable. This allowed outer planets to accumulate far more mass, as ice contributed additional solid material to growing cores. The distribution of rocky terrestrial planets inward and gas and ice giants outward reflects this early thermal structure. The solar system's architecture carries the imprint of those temperature gradients. From inner rocky worlds to distant icy bodies, composition still echoes the heat map of a long-vanished disk. Not every object in the solar system rotates smoothly like Earth. Some asteroids spin in complex, tumbling motions rather than along a single stable axis. This behavior is known as non-principal axis rotation. Tumbling can occur after collisions or gradual torque from uneven heating by sunlight. Instead of maintaining a simple day-night cycle, these bodies rotate unpredictably, their orientation shifting over time. In the vacuum of space, there is little friction to slow or stabilize such motion. Once set into a tumble, an asteroid may continue that complex rotation for millions of years. Even rotation, something we often imagine as steady and uniform, can become intricate. The solar system contains not only orderly spins, but irregular evolving motions shaped by ancient encounters. The outer planets, Jupiter, Saturn, Uranus, and Neptune, may have assembled relatively quickly in the early solar system. Beyond the snowline, ices contributed additional solid mass to growing cores, allowing them to reach critical size before the solar nebula dissipated. Once these cores became large enough, they could rapidly accumulate surrounding gas, forming thick envelopes of hydrogen and helium. Timing was essential. The protoplanetary disk did not last indefinitely. In contrast, the rocky inner planets formed in a region where less material was available. Their growth proceeded more slowly through repeated collisions and mergers. The size and composition differences between inner and outer planets reflect this early divergence in formation pathways. Speed and location shaped destiny. While rings may appear delicate and ornamental, they can originate from dramatic events. If a moon drifts too close to its planet, tidal forces can overcome the moon's structural integrity. The result is fragmentation, with debris spreading into orbit. Within a certain boundary, known as the Roche limit, gravity prevents fragments from reassembling into a single body. Instead, the material remains dispersed, forming a ring system. Over time, rings can evolve. Particles collide, spread, and sometimes migrate. Some may eventually fall inward, while others move outward. Rings are not necessarily primordial. They can be the remnants of destruction, reshaped into shimmering structures by gravity and orbital mechanics. The visible disk of the Sun marks only the photosphere. Above it lies the chromosphere and then the corona, layers that extend millions of kilometers into space. The corona is faint and normally invisible, but during total solar eclipses it appears as a pale halo surrounding the darkened Sun. It consists of extremely hot plasma structured by magnetic fields. Though tenuous, this outer atmosphere blends gradually into the solar wind, which streams outward across the solar system. The Sun does not end abruptly. Its atmosphere fades outward, thinning until it merges with interplanetary space. The star's influence is layered, radiating outward in gradients rather than sharp edges. Not all bodies in the solar system orbit neatly within the ecliptic plane. Some distant objects follow paths significantly tilted relative to the main planetary disk. These inclinations may be the result of past gravitational interactions, scattering events, or early planetary migration. Once placed on inclined orbits, many of these objects remain stable for billions of years. The solar system's overall flatness reflects its disk-like origin, but variation persists. Tilted paths introduce vertical structure to what might otherwise seem a two-dimensional arrangement. Even within a largely ordered plane, diversity of inclination adds depth to the architecture of motion. Far beyond the known planets lies a vast, spherical distribution of icy bodies often referred to as the Oort cloud. Though not directly observed, its existence is inferred from the long, elongated orbits of certain comets that arrive from every direction in the sky. These distant objects may extend nearly a light-year from the Sun. They are weakly bound by gravity, so distant passing stars or subtle galactic tides can gently disturb them. When perturbed, a comet may begin a slow inward journey that lasts millions of years before it becomes visible near the Sun. The Oort cloud represents the outermost reach of solar influence in terms of small body populations. It is less a structured ring and more a distant reservoir, a halo of frozen remnants drifting at the boundary between stellar and interstellar space. During a total solar eclipse, when the Moon perfectly covers the Sun's bright photosphere, delicate structures in the corona become visible. Streamers extend outward in graceful arcs, tracing magnetic field lines. These structures vary with the solar cycle. At solar minimum, the corona appears more elongated along the Sun's equator. At solar maximum, it becomes more symmetrical, reflecting widespread magnetic activity. The corona's intricate filaments are shaped by magnetic forces rather than by physical surface features. They demonstrate how invisible magnetism sculpts plasma into luminous geometry. For a few quiet minutes during totality, the Sun's outer atmosphere reveals its hidden structure, a soft halo suspended against the darkness of space. While dust storms were mentioned earlier in another context, their scale is worth understanding more deeply. On Mars, small local storms can merge and expand, sometimes enveloping the entire planet in a haze that lasts for weeks or months. The thin atmosphere allows fine particles to remain suspended for long periods. Sunlight heats the dust, which warms the surrounding air, driving stronger winds that lift even more dust. This feedback loop enables storms to grow to global proportions. Unlike Earth's storms, which are shaped by oceans and moisture cycles, Martian dust storms are driven largely by dry thermal dynamics. The planet's surface and atmosphere interact in delicate balance, allowing fine red particles to reshape the sky itself. The immense gravity of Jupiter does not simply hold its moons in orbit. It continuously pulls and releases them as their orbital distances vary slightly. This tidal flexing generates internal friction and heat. On some moons, this heating is sufficient to drive geological activity. On others, it may sustain subsurface oceans beneath icy crusts. The magnitude of tidal influence depends on orbital eccentricity and resonance relationships. Gravity, in this context, becomes a source of warmth rather than compression alone. Though the outer solar system is far from the Sun's heat, tidal forces provide an alternative energy source. Within these rhythmic stretches and releases, internal motion continues quietly beneath frozen surfaces. The center of mass of the solar system, called the barycenter, does not always lie at the center of the Sun. Because Jupiter is so massive, the barycenter can sometimes reside just outside the Sun's visible surface. As planets orbit, the Sun itself moves in a small, complex path around this shared center of mass. It does not remain perfectly fixed. Instead, it wobbles slightly in response to planetary positions. This motion is subtle but measurable. It reflects the principle that gravity is mutual. Even the most massive body in the system responds to the pull of its companions. The Sun leads the dance, but it also participates, shifting gently as the planets trace their paths around it. When we picture the asteroid belt, it is tempting to imagine a crowded field of tumbling stones, but in reality the belt is mostly empty space. The average distance between sizable asteroids can be hundreds of thousands to millions of kilometers. If you were to pass through the belt in a spacecraft, the chance of collision would be extraordinarily small. Even its largest members are separated by vast expanses of vacuum. The belt's total mass is only a small fraction of Earth's moon. Its apparent density is an illusion born from diagrams and science fiction. In truth, it is a sparse region, a scattering of remnants that never coalesced into a planet. Between Mars and Jupiter lies not a barrier of stone, but a quiet region where fragments orbit with generous room to spare. Although far in the future, the Sun's evolution is already determined by stellar physics. In about 5 billion years after exhausting hydrogen in its core, it will begin to expand into a red giant. During this phase, its outer layers will swell outward, engulfing or scorching the inner planets. Its surface temperature will cool even as its total luminosity increases. Eventually, it will shed its outer layers into space, leaving behind a dense core known as a white dwarf. This transformation is not sudden. It unfolds over millions of years. Stars age slowly, governed by internal fusion rates and gravitational balance. The Sun's present stability is one chapter in a much longer stellar life cycle, stretching far beyond human timescales. On rare occasions, objects from outside our solar system pass through it. These interstellar visitors are not gravitationally bound to the Sun. Instead, they travel on hyperbolic trajectories, entering and exiting once before continuing into deep space. The first confirmed example was detected in 2017. Its unusual speed and trajectory revealed that it originated beyond our system. Such objects carry materials formed around other stars. These passages are brief. The Sun's gravity alters their paths slightly but does not capture them. They remind us that planetary systems are not isolated islands. Occasionally, fragments from distant stars cross our neighborhood, offering fleeting glimpses into other stellar environments. Though elliptical in principle, Earth's orbit is remarkably close to circular. Its eccentricity is low compared to planets like Mercury or many dwarf planets in the outer system. This near-circular orbit contributes to relatively stable solar energy distribution throughout the year. Seasonal variations arise primarily from axial tilt rather than dramatic changes in distance from the Sun. In contrast, some distant bodies experience significant shifts in solar heating as they move along elongated paths. Earth's gentle ellipse provides climatic steadiness. The geometry of orbit shapes environmental stability, influencing long-term conditions for life. All 8 major planets orbit the Sun in the same general direction, counterclockwise when viewed from above the Sun's north pole. Most also rotate in that same direction. This shared motion reflects their origin in a rotating protoplanetary disk. As material coalesced, it preserved the angular momentum of that disk. The alignment is a fossil of formation. There are exceptions in rotation and tilt, shaped by later impacts or gravitational interactions. But the overall coherence remains. The planets move together, like leaves carried along by the same slow current. Even billions of years later, their direction of travel tells the story of a common beginning. On certain worlds, faint glows appear in the upper atmosphere even in darkness. These are called air glow emissions, and they occur when atoms and molecules excited by sunlight during the day slowly release energy at night. On Earth, this glow is subtle and usually invisible to the naked eye. But on other planets, including Mars and Venus, orbiting spacecraft have detected delicate layers of light tracing atmospheric chemistry. Airglow is not dramatic like auroras, it is soft and persistent, the quiet afterimage of daytime radiation. Even in shadow, atmospheres continue to emit light. The night side of a planet is never entirely dark. Energy absorbed earlier lingers, released gradually as a faint shimmer high above the surface. Carbon-rich asteroids and comets contain complex organic compounds, long chains of carbon-based molecules formed in the cold outer regions of the early solar nebula. Some of these compounds are delivered to planets through impacts. Meteorites recovered on Earth have been found to contain amino acids and other organic materials. While not evidence of life themselves, they demonstrate that prebiotic chemistry occurs naturally in space. The building blocks of more complex chemistry are not confined to planets. They formed in the cold darkness long before Earth developed oceans or atmosphere. The ingredients for life were present early, carried within drifting bodies that moved quietly between worlds. Jupiter's immense mass allows it to influence the paths of comets and asteroids. In some cases, it deflects incoming objects away from the inner solar system, reducing potential impacts on the terrestrial planets. In other cases, however, its gravity can redirect bodies inward, sending them toward the Sun or the inner planets. Its influence is not purely protective nor purely disruptive. It is dynamic. Over billions of years, Jupiter has shaped the distribution of small bodies throughout the solar system. Its presence has altered orbits, created resonances, and influenced impact rates. As the largest planet, it participates actively in the gravitational evolution of its surroundings. Though lacking thick gaseous envelopes, certain icy moons possess extremely thin atmospheres, sometimes formed by surface sublimation or sputtering from charged particle interactions. For example, tenuous layers of oxygen or water vapor can exist temporarily above icy crusts. These atmospheres are delicate and constantly replenished or lost. They are not stable like Earth's atmosphere. Instead, they fluctuate with temperature and radiation. Even small bodies can maintain momentary halos of gas. Atmospheres need not be thick to exist. Even a whisper of molecules counts. The Sun is one star among hundreds of billions in the Milky Way. Within a few dozen light years lie numerous neighboring stars, some with planetary systems of their own. The solar system does not drift alone. It moves within a stellar neighborhood shaped by shared galactic rotation. Over millions of years, the relative positions of nearby stars slowly change. Though distances are vast, gravitational influences from passing stars can subtly perturb distant comet reservoirs. The solar system is embedded within a dynamic galactic environment. Our planetary home is local, but not isolated. Even a planet with gravity as strong as Earth's cannot hold every particle forever. At the very top of the atmosphere, in the exosphere, individual atoms sometimes move fast enough to escape into space. Hydrogen, being the lightest element, drifts away most easily. This process is slow and continuous. Earth loses thousands of tons of hydrogen each year, yet it is replenished through chemical reactions in the lower atmosphere and from volcanic processes. The loss does not threaten the planet's stability on human timescales. Still, it is a quiet reminder that atmospheres are not sealed containers. They are dynamic boundaries between world and vacuum. Over immense spans of time, molecules can slip away, crossing the invisible threshold from planet to space. The Sun's magnetic influence stretches outward, carried by the solar wind into interplanetary space. This field does not remain straight. Because the Sun rotates, the outward flowing magnetic lines twist into a spiral pattern known as the Parker spiral. As the solar wind streams away, the magnetic field is drawn into gentle arcs that wind through the solar system. Spacecraft traveling between planets must navigate this magnetized environment. The spiral structure demonstrates how rotation and outward motion combine. The Sun's spin imprints a subtle curve into space itself. Even far from the visible surface, magnetic structure persists, shaping plasma flows across billions of kilometers. Compared to outer worlds, the inner planets contain relatively little hydrogen, helium, and other light volatile compounds. During the early solar system, high temperatures near the young Sun prevented these elements from condensing into solid form. As a result, rocky planets formed primarily from heavier materials, silicates, and metals. Volatiles were either blown away by solar radiation or remained in gaseous form farther out. This early temperature gradient influenced planetary composition permanently. The distinction between terrestrial and giant planets reflects not only size but chemical availability. The materials present during formation shaped each world's character. A planet's brightness depends on its albedo, the fraction of sunlight it reflects. Venus reflects a large portion due to its thick cloud cover, making it one of the brightest objects in the sky. Mercury, in contrast, is darker despite its proximity to the Sun. Albedo influences temperature as well. Highly reflective surfaces absorb less solar energy. Darker surfaces retain more heat. Across the solar system, reflectivity varies widely depending on composition, ice coverage, and atmospheric properties. Brightness is not simply a matter of distance. It is also a function of surface and atmospheric chemistry. The way a world shines reveals something about its structure and materials. Inside the Sun, energy travels through distinct zones. In the inner radiative zone, energy moves outward primarily through the repeated absorption and re-emission of photons. In the outer convective zone, hot plasma rises and cooler plasma sinks in circulating currents. These layers are not visible directly, but they can be studied through helioseismology, the observation of waves rippling across the solar surface. By analyzing oscillations, scientists infer internal structure. The Sun's interior is not uniform. It is stratified by physics, shaped by pressure, temperature, and density gradients. Beneath the smooth glow lies a layered engine, operating steadily across billions of years. Not all worlds are spherical. Some dwarf planets and large icy bodies rotate quickly enough that centrifugal force slightly elongates them. Haumea, for example, completes a rotation in just a few hours, causing it to take on an elongated oval shape rather than a perfect sphere. Rapid rotation redistributes mass. The equator bulges outward while the poles flatten slightly. Over time, this reshaping becomes permanent if the body's material can deform under its own gravity. Rotation is not just a measure of time, it influences structure. Even distant icy worlds respond to spin, adjusting their shape in quiet obedience to physics. Geometry reflects motion, and motion leaves its mark. The Sun converts about 4 million tons of mass into energy every second through nuclear fusion. Though that number sounds immense, it represents only a tiny fraction of the Sun's total mass. Fusion in the core is regulated by a balance between gravity pulling inward and pressure pushing outward. If fusion rates increase slightly, the core expands and cools, slowing the reaction. If they decrease, gravity compresses the core, raising temperature and restoring equilibrium. This feedback creates long-term stability. The sun does not flare unpredictably in total brightness. Its output remains steady over millions of years. Our star's calm radiance is not accidental. It is the product of self-regulating forces maintaining balance deep within its core. The plane in which most planets orbit, the ecliptic, is not perfectly aligned with the plane of the Milky Way galaxy. Instead, it is tilted by about 60 degrees. This means that when we look at the Milky Way arching across the night sky, we are viewing it from an angle not directly aligned with our planetary disk. The orientation of our solar system was determined by the spin of the original molecular cloud that formed it, independent of the galaxy's broader rotation. Even within a larger structure, local orientation can vary. The solar system carries its own axis of alignment, distinct from the galactic plane. We orbit the sun in one flat geometry while the sun orbits the galaxy in another. According to general relativity, gravity influences time itself. Clocks closer to massive objects tick slightly more slowly than those farther away. In the solar system, this effect is measurable, particularly near the sun. Spacecraft navigation systems and high-precision instruments must account for these subtle time differences. Even Earth's satellites experience tiny relativistic adjustments to maintain accuracy. The curvature of space-time is not dramatic in our planetary environment, but it is real. Gravity shapes not only motion and orbit, but duration. The steady ticking of time is gently modulated by mass. When we look at the night sky, the solar system appears steady and permanent. The planets follow familiar paths. The sun rises and sets with reassuring regularity. Yet beneath that calm repetition, motion continues in subtle ways. Orbits are not locked in place forever. Gravitational interactions exchange tiny amounts of energy between bodies. Moons slowly migrate. Small asteroids are nudged into new trajectories. Even the sun itself responds slightly to the pull of its planets as they circle their shared center of mass. On human timescales, these changes are imperceptible. The structure feels solid. But across millions and billions of years, stability does not mean immobility. It means balance within gradual adjustment. The solar system endures not because nothing changes, but because change unfolds gently, guided by gravity, time, and the quiet conservation of motion. And among those slow transformations, even the strength of the sun's gravitational hold is not perfectly constant. Every second, the sun converts millions of tons of mass into energy. That mass does not vanish without consequence. Through fusion and the steady outward flow of the solar wind, the sun is gradually becoming lighter. The change is extraordinarily small on human timescales, but gravity depends on mass. And as the sun slowly loses it, its gravitational hold weakens ever so slightly. Over billions of years, this causes the planets to drift outward, inch by inch, into slightly wider orbits. Earth will move farther from the sun. So will Mars. So will the outer giants. The architecture of the solar system expands in response to this subtle release. It is not a dramatic unraveling. It is a gentle easing. The same star that once gathered dust into planets will, in its long middle age, allow those planets to breathe outward. Distance increases gradually, almost tenderly, a slow loosening written into the physics of fusion itself. And so, even in stability, there is motion. Even in constancy, there is quiet release. The sun burns. The planets turn. Orbits widen by distances too small to notice tonight. Nothing breaks. Nothing rushes. The balance simply adjusts. You are resting on a world that circles a star, slowly giving a part of itself away. Light into space, gravity softening across eons. The system endures not because it is frozen, but because it changes gently. Let that be enough for now. The orbits will continue, the light will arrive, and you can drift into sleep beneath their steady, widening paths.